Good afternoon. Welcome to today's chemistry lecture. In today's lecture, we will start off with laws of chemical combination. So let me write that down here. Laws of chemical combination. Now, the first law we will be discussing would be the law of conservation of mass. Now, this law was proposed by the French chemist Antoine Laurent Lavoisier in 1789. Now, what this law basically said was mass can neither be created nor be destroyed. Now, what this means is if you take the mass of all the reactants in an equation and if you take the mass of all the products formed, both of them should be equal. Mass cannot magically appear or disappear from a reaction. Every gram, milligram should be accounted for. Now, let us write that down here. One, one. Law of conservation of mass. Law of conservation of mass. Now, let's write the date here, year here as well. It was in 1789. Now, we will write a small description of this. So, matter can neither be created nor be destroyed. Matter can neither be created nor be destroyed. Now let's take an example. I am sure all of us understood this, but still we'll take an example. Let's take mercury oxide. Now, if we take 100 grams of mercury oxide and we heat it, we get mercury and oxide. This is called a decomposition reaction because we have one reactant and we are splitting it down into its individual elements. So mercury plus oxide. Now, if it's given that we get 92.6 grams of mercury, we can easily find out how much of oxide or how much of oxygen we get. How much of oxygen we get. According to the law of conservation of mass, total mass in a reaction would be constant. So we can just subtract 92.6 from 100 and we get 7.4 grams. So 7.4 grams. Good. Now, on to law number 2, law of constant proportions. Now, this law was stated by J. Prost in 1799. So this is exactly 10 years later. Now, what this law said is a chemical a chemical compound, irrespective of its source, always contains fixed proportions of its elements by mass. Now, by mass is the important part. So let me write that down here as well. I'll pick green. Now, number 2, law of constant proportions. Now, this was given exactly 10 years later. So it's 1799 now. Now, what this law says is uh, chemical compound irrespective of its source always combines uh, in fixed proportions of its elements by mass. in fixed proportions of elements by mass. Fine. Okay, so as an example, let's take CO2 here. I will take this in red. So if we have CO2. Now there are various ways of forming CO2. If you take now one way of forming CO2 would be take carbon, add oxygen gas, and we get CO2. Another way is taking a hydrocarbon. So hydrocarbon, and we burn it in oxygen. We get water and carbon dioxide. And another way of preparing carbon dioxide is you take calcium carbonate and you heat it. Again, this is called a decomposition reaction. You heat it, you get calcium oxide and carbon dioxide. Now, all three forms of carbon dioxide here will have exactly the same, will combine to, or carbon and oxygen will combine in these cases to form carbon dioxide in the exact same ratio. So no matter the source, irrespective of the source of the compound, it will always contain fixed proportions of its elements by mass. So all three are CO2. Now the ratio of its masses would be mass of C is 12 and mass of oxygen is 16. So 16 to the 32. So we get 3 is to it. Fine. Now the next law we will learn about is law of multiple proportions. So let me scroll down, take green, you know the drill. Uh, Law of multiple proportions. Now, this law was given by Dalton, and we always write the year here. So it was given in 1803. Now, what Dalton said was when two elements combine with each other to form two or more than two compounds, the mass of one of the elements, which combines with the fixed mass of the other, bears a simple whole number ratio. Now, again, it's a very big statement to write. I hope all of you have understood that. I will say it again. So when two elements combine with each other to form two or more compounds, so that's two. So for example, let's take carbon, I'll take this in red. Let's take carbon monoxide. Red, I said red. Okay. Yeah, carbon monoxide. And let's take carbon dioxide, CO2. Now, in this, we have 12 parts by mass of in carbon monoxide. We have 12 parts of mass of carbon with 16 parts of mass by oxygen. So I'll narrow and I'll say 12 parts. This is by mass, I mean 12 parts carbon, 16 parts oxygen. Now, if you look at CO2, we again have 12 parts of CO2 and we have 32 this time, 32 parts of oxygen because we have two oxygen molecules. Now again, the ratio of the masses of the oxygen, which is combined with the fixed mass of carbon. Now if you see, both these elements have the same number of carbon atoms. We have C and we have C. For both, we have one in both cases. Now, so the ratio of the other element, which is combining with this fixed number of the fixed mass of carbon here, is oxygen. And again, all this law is saying is the ratio of these two oxygen atoms, the oxygen atom in carbon monoxide and the oxygen molecule in carbon dioxide will be a whole number ratio. So if you look here, mass of O is 16, mass of O2 will be 32. So this will be in a whole number ratio, 1 is to 2. Now I'll do a quick revision of this. This is a slightly harder concept we have here. So the ratio of masses of oxygen, it combines with the fixed mass of carbon. Now we have fixed mass of carbon because both carbon monoxide and carbon dioxide have one carbon atom. Fixed mass of carbon in these elements is 1 is to 2. Again, what this law basically says is the element which is not constant, which has different number of atoms in each compound, that ratio would be a whole number ratio. So again, we have in carbon monoxide, we have 16 parts oxygen, carbon dioxide, we have 32 parts oxygen. Now this is a whole number ratio, we get 1 is to 2. Okay. Now let's move on to the next law that we will study, which is Gay-Lussac's law of gaseous volumes. Now what this law basically says is in a chemical reaction, gases combine together in the simplest ratio of their volumes. Now we are using volumes here because we are talking about gases. Their volumes, provided that all gases are at the same condition of temperature and pressure. Now this is a fairly easy concept to understand. Let me just write that down. Number 4, we have Gay-Lussac's law. So Gay-Lussac's law of gaseous volumes. It has gaseous in the name. Gaseous volumes. Now this was given in 1808, 5 years later. Now what this law says is gases combine in a simple ratio by volume. So write that down. Gases combine in a simple ratio by volume. Now let's take an example of NH3 here. Okay, so how you make NH3 is, as the name suggests, you need hydrogen gas and you need nitrogen gas. So that's N2 plus H2 gives NH3. Now if you see, this equation is not balanced. We have 2 nitrogen atoms here, but you only have 1 here. So let's put it 2. But now we have 6 hydrogen atoms here, but only 2 here. So we'll put it 3. So 3H2 plus N2 gives 2 NH3. Now hydrogen and nitrogen will combine in the ratio 3 is to 1 to give us 2 moles of NH3. So 3 is to 1 will give us 2. Now this ratio remains constant. It will only, and I mean only, combine in this ratio to form NH3. That was pretty simple to understand, I hope. We'll move on to Avogadro's law. Now, as we all know, we produced Avogadro's number, which is 6.022 into 10 to the power 23. It is the mole number. It is also known as Na. It's a very useful number. Now, what Avogadro says is equal volume of all gases under identical conditions of time, temperature, and pressure would contain equal number of molecules. Now, so if we take, okay, let me write that down here. Fifth, that is not green. Fifth. Avogadro's law. Now, my man said this in the year 1811. My man said this in the year 1811, Avogadro. Now, here is his entire argument. The smallest particle of an element that takes part in a chemical reaction is called an atom. Now, it may or may not have independent existence. The smallest particle of a substance, which is an element and a compound, that has independent existence is called a molecule. Now, he argued that since the smallest particle of gases that has independent existence is a molecule and not an atom, hence the volume of gases should be related to the number of molecules and not number of atoms. Now he put forward Avogadro's law. It states that equal volumes of all gases under similar conditions of temperature and pressure would contain equal number of molecules. So let me write that statement here. Equal volume of all gases under similar conditions of temperature and pressure under similar conditions of temperature and pressure contain equal number of molecules. Equal number of molecules. So let's take an example here. We have hydrogen plus chlorine, which gives us hydrochloric acid. So H2 plus Cl2 gives us HCl. Now to balance this equation, we will simply just put 2. So it works now. We have 2 atoms of hydrogen, 2 atoms of hydrogen on the right, 2 atoms of chlorine, and then 2 atoms of chlorine on the right. Now what this one said is 1 molecule of NH3, 1 molecule of H2, hydrogen gas, will combine with 1 molecule of chlorine to give us 2 molecules of hydrogen carbon. Hydrogen chloride, 2 molecules of HCl, hydrogen chloride, provided the temperature remains constant and the pressure remains constant as well. So, man, there's a Na, so 1 mole of this plus 1 mole of this will give you 2 moles of this. Again, it will have combined in a definite ratio. Equal volumes of all gases under similar conditions of temperature and pressure contain equal number of molecules. Now I will write Avogadro's number here as well because it's a very important number and you will use it throughout chemistry. So Na is equal to 6.022 into 10 to the power 23. Okay. So that is it for today's lecture. Thank you.